Hey everyone, I wanted to do a video lesson for section 7.7, the trapezoid and Simpson rule. So this is something I'm going to try. You're going to have to bear with me and see if it works. I already wrote the notes and just going to go over them. And for Simpson's rule, I'm going to write them as I go for the next video. So just kind of let me know what you guys like, what you prefer, or if it doesn't matter. So just bear with me as we go through this. So trapezoid rule, we did this problem in class. I started to explain it, so I'm just going to go through the setup really quickly. The main purpose of the formulas, trapezoid and Simpson's rule, is to give us a way to approximate the value of a definite integral when the function cannot be integrated by our regular methods, right? We can't do substitution, we can't do integration by parts, we can't do trig, sub, we can't do partial fractions, we can't do any of those things. So we want to be able to estimate it. So some examples of integrals that cannot be done are these two. There are way more, but those are the ones I put as an example. The example we worked on in class, and if you look at your notes from before, was the integral from 1 to 3 of 1 over x dx, and we're going to use 4 trapezoids. So the exact value, without doing the approximation, is we actually integrate it. And this is an elementary function, so the integral 1 over x is just natural log absolute value of x, and we evaluate it. Remember, the natural log of 1 is 0, so that goes away, so we're just left with the natural log of 3, which is 1.0986. So using 4 trapezoids, just like we talked about with rectangles, first thing is to find your delta x, and delta x is b minus a over n. So in this case, 3 minus 1 over 4, since we're using 4 trapezoids, which ends up being 1/2. And I wrote out what the function looks like with our endpoints, delta x, and so to get from the beginning endpoint, remember our integral is from 1 to 3 of 1 over x dx, so we start at 1, and then you add delta x to get to the next value. So that's what this plus 1/2 means. We're adding delta x every time. And the area of a trapezoid, recall, is 1/2 base 1 plus base 2, the whole thing times the height. And I did this in class the last time we met before the exam. And so for the first trapezoid, the area will be 1/2 f of x1 plus f of x2 times the height, which is delta x. Remember, our trapezoids are kind of standing up instead of how we used to seeing them on the side. The total area approximation is the sum of the 4 trapezoids. So I wrote them out here. 1/2 b1 plus b2 times the height. The height is delta x. So that's where that 1/2 is coming from. That's your delta x. For the second trapezoid, f of 3/2 plus f of 2, 1/2, and delta x again. The third trapezoid, and finally the fourth trapezoid. Factor out common values. The common values are the 1/2 from the formula and the delta x, which happens to be 1/2 as well. And what you're left with is all the stuff that's in the brackets inside. So f of 1, you have f of 3/2 plus another f of 3/2 gives us 2 of those. F of 2 plus another f of 2 gives us 2 of those, and so on, until the only one that doesn't repeat is the very last one, f of 3. So notice that f of 1, the first one, so your f of a, and f of 3, the last one, f of b, doesn't repeat. And so putting this all in, remember that our function is 1 over x, so when I do f of 3/2, f of 3/2 is really 1 over 3/2, which gives me the reciprocal, 2/3. F of 2 is 1/2, f of 5/2 is 2/5, f of 3 is 1/3. And then compute all that out. I put it in my calculator, and this is what I got. If you get something else, let me know, but I double checked it. So therefore, the integral approximation is 1.1167. And we knew from the previous page, our actual was 1.0986. So my question is, what is the error? And there are a couple things we can do. We can find the absolute error in our approximation is the absolute value of the actual minus the approximation. The reason we do the absolute value is because sometimes you're going to overestimate and sometimes you're going to underestimate, but we just want to know the size of the error. And so in this case, we have 1.0986 minus 1.1167, so this is an over approximation, which means this is a negative number on the inside, but you take the absolute value. So it's 0.0181. The percent error is the error we found above, the absolute error, divided by the actual, which is the actual was 1.0986 from our integral, and you get this when you convert it to a percent, multiply by 100. So which is a pretty good approximation, not the best, but it's not the worst either. But we won't always be able to compute the integral. Remember, e to the x squared cannot be integrated. So how would I find the error if I don't have the actual? The error estimation in our approximation using the trapezoid rule is this formula. And I can go into more detail about this, but not right now. So the error, the actual error, is less than the approximate error, the error in the estimation. So for a less than x less than b, so this x is between a and b. So our a and b are 1 and 3. Now this is the part that's tricky. The maximum of the absolute value of the second derivative. That's what that means. So let's see what that formula looks like. We're going to use that formula to find the error in our approximation of that integral. So this is the actual error, and we're saying it's less than. This is the error in estimation, the formula. So we know a, b, n, and f of x. B is 3, a is 1, n is 4. And we know f of x, but this whole quantity is kind of intimidating. This is the trickiest part. So we need to find the maximum of the absolute value of the second derivative on AB. Remember, for our particular problem, this will say 1 less than or equal to x less than or equal to 3 for this function. So we know f of x is 1 over x. We can write it as x to the minus 1 since we need to take the derivative. Take the derivative, but we need the second derivative, so take that also. That's what this is, 2 over x cubed. And we need to take the absolute value. Notice that the formula says the maximum of the absolute value. So the absolute value on 1, 3, 1 and 3, that interval is of positive values, so that's going to remain positive. So we can essentially just drop the absolute value. So the maximum of the absolute value of the second derivative is really just the maximum of the function 2 over x cubed. So when is this the largest, right? We want to find the maximum. When is it the largest? And there are 3 ways that we can do this. We can do it by just analyzing the function. On 1, 3, 2 over 1, right? Remember, our function is 2 over x cubed. So 2 over 1 cubed is larger than 2 over 3 cubed. 2 is larger than 2 27ths. So the maximum occurs at 1, and the maximum is 2. So now that I know the maximum is 2, we can go back to this formula and put it in there. But I'm going to show you the other 2 ways. Second way is you can use your knowledge from Calc 1. Use Calculus 1 to find the absolute maximum on a closed interval, right? This is now our function. That's the absolute value of the second derivative. So I'm going to call it something else. Let big F be that function, and write it like that because I need to take the derivative, and find critical numbers. Right? Critical numbers happen where the derivative is 0 on the fine. The critical number is x equals 0, but that's not even in the interval 1, 3, so we don't worry about it. Plus it's on the fine, so we wouldn't worry about it anyway. Because remember, the maximum or minimum occur at a critical number, not where the derivative is 0, not at a critical number where the derivative is undefined. So a max occurs at an endpoint, and we know it's at 1. And again, you can do it by just looking at it. It happens at 1. Not by looking at it, sorry, by doing the chart. So 1, 3, and we have no critical numbers. No critical points to check, so we just check the function. So this will be 2 over 1, which is 2, and this will be 2 over 3 cubed, which is 2 over 27, so that will be the max. Methods from Calc 1. Now, draw a graph. The third way is draw a graph of 2 over x cubed, the absolute value of the second derivative from the original function. And when I drew it on my TI-84, this is what I came up with. And notice that this function is decreasing, so the maximum is going to occur at the left endpoint, which is 1, and the maximum is 2. So all 3 ways we get that the maximum is 2. So let's go back to the error formula. We had already had b minus a cubed 12 n squared, and now the maximum of the second derivative, we just found it to be 2. And when you multiply all that out, we get 112, which is 0.0833. The actual error is 0.0181. Remember, we did that earlier when we found the integral. And I lost my page, but when we found the integral, this was the actual area, and then we did the trapezoid estimation, and that's how we got our actual error was 0.0181. So now the actual error is 0.0181. The error estimate is this guy, 0.0833. So the actual error should be less than the error estimate, which it is. This was our actual, the error in the trapezoid rule, and this was our estimate. 0.0181 is definitely less than 0.0833. So this is true. In general, the trapezoid rule formula is the integral from a to b of f of x dx is approximately Tn. That's the notation that we use to say the trapezoid rule is being used, with n being the number of trapezoids. So for our example, we used T4 because we had 4 trapezoids. So it's 1/2 times delta x f of x1 plus 2f of x2, 2f of x3, and so on. They all have 2's except for the last one, where delta x is your b minus a over n, and the actual error is less than, this is the error estimate. And remember, the trickiest part is finding the maximum of the second derivative. And now what I want you to do is I want you to try it on your own to approximate the integral from 0 to pi of sine x dx using 4 trapezoids. If you want, you can also do it using 8 trapezoids and see which one is closer. Obviously with n equals 8 is going to be closer, but what's the error in both of them? Find the exact error, actual minus approximation, and also the error estimate, this guy, that formula. And I will post the answer later. I'm gonna do an example using Simpson's rule and explain what Simpson's rule is. Email me if you have any questions.